Good morning, everybody. Um, Today is something that's not going to be in your packet. You're going to want to have probably 2 pieces of notebook paper. So dig something out, because what we're going to talk about today is simplifying square roots. And simplifying square roots is one of those things in the book that they have this little blurb on it, but you have to know how to do it in order to accomplish what we have to for objectives in 4.6, 4.7, and 4.8. So we have to know how to do this, but not enough to make it a full packet of anything. So here's how we're going to start. We know the brain is this fabulous little machine. And here's another thing that we know about the brain. If we have to look something up, our brain says, gosh, maybe I better remember this for the future. And sometimes it'll move it to your long-term memory. But if we punch it into the calculator, a lot of times our brain just shuts off. So what we want to do is force our brain to start to remember some of the perfect squares. So if you have a blank sheet of notebook paper, you don't need the whole thing. You maybe just need a strip of it. When we were in class, I always gave people a colored strip of paper, because what we want to do is we want to write down those perfect squares again. We did this in one of the other sections, but this will be kind of like a bookmark. And whenever you're doing your homework and you're thinking, oh, what was that perfect square that I needed again? You'll pull this out, and the more that you have to look it up, the more your brain is going to say, oh, for goodness sake, I'll just remember this one. I don't want to have to look it up anymore. So 1 squared doesn't help us. It's just 1. But let's go ahead and write down on that little strip of paper that you'll use as a bookmark for your homework, let's at least go to 15 squared. And I would just do all of it vertically and just keep going until you get to 15 squared. Oh, maybe I better write them down though if somebody forgot them. So like I said, and this little strip that you use as a bookmark, you can't use it on the test, but that's not the point. The point is our brain does better when we have to physically look something up. It's like there's a physical attachment to it. And our brain says, oh, for goodness sake, I don't want to look up 15 squared anymore. Just remember it's 225. And we go from there. Does anybody need more time to write down the perfect squares from 1 squared to 15 squared? If you do, unmute and let me know. Those of you that just joined a little bit later, this is not going to be a lesson that's in your packet, so you're going to need at least 1 sheet of paper to go through this. And what I'm advising everybody to do is to cut off a strip of a piece of paper and write down all those perfect squares and use those as a bookmark for when you go to do your homework, because it's going to force your brain to say, I need to remember this. So let's go ahead and write down 1, which is the square root of 90. Now, if we have to simplify the square root of 90, we've already talked in the past about how that means we have to factor out any of these nice perfect squares that go in there. And it's not just any of those, it would be the biggest one. So here's what I do. I think about where 90 would fit in this list. And 90 would be right there between 81 and 100. And then just kind of work backwards in your head. Would 81 divide into 90? No, not evenly. 64? 49? Nope. 36? Nope. 25? Not in the 90. 16? Nope. 9. So 9 is the largest perfect square that will divide into it evenly. And square roots can only be multiplied by other square roots. So when we break this apart and we say it's the square root of 9 times the square root of 10, it absolutely is, because we could multiply these back together and we could get 90. Now let's just say I wasn't sure if I found the biggest one. Well, then I look at 10 and I say 10 would be about right here. Can I divide 10 by 9 or 4? Because those are the only ones that are helpful. And the answer is no. So I did find the biggest one, so I don't have to keep going. And then the reason I picked 9 is because the square root of 9 is 3. I want these nice perfect squares to come out of my, well, there's different names. I think we talked about this, though. This is called a radical, and the 90 is called the radicand. So radical for the whole thing, radicand for the 90. It's 3. Square root of 10, there's nothing else I can do with that. No perfect squares are going to go in there. But this is now simplified because of that, because all the perfect squares are out of there. So I want somebody to unmute. We'll call this problem 1.5. And help me with the square root of 50. So think about your list, and somebody unmute and give me the biggest perfect square I can use for that one. 25. Yes. And because the square root of 25, the 25 is on our list over here as a perfect square, the square root of that will be 5. So we'll get 5 square roots of 2. All right, now, each of these gets a little more complicated than the last one. This isn't just the square root of 72. It's 8 times the square root of 72. So now I start thinking, 72 is a pretty big number. There ought to be something from those perfect squares that goes into 72. But I'd also like to get the biggest one. So let's see. 72. Well, 8 squared is 64. But 64 is not going to go into that. 7 squared is 49. That's not going in there either. 6 squared is 36. Oh, that goes in there twice. So now I have the largest one, because probably a lot of you were saying to yourself, 9 and 8. Well, 9's a perfect square, but 8 we can still divide by 4. So that's not going to be the biggest perfect square that we can pull out. And we know the square root of 36. It's 6. And now what we have to remember is that 8 that's in front, in algebra, when things are sitting right next to each other, that means multiply. Well, these are both integers now, so we can multiply the 8 times the 6 now that the 6 doesn't have a square root anymore. And we'll get 48 square roots of 2. So the number that's out in front, remember, that's going to be multiplying. Let's try one of those as well. We'll call it problem 2.5. 3 square roots is 75. Somebody unmute and tell me how we should break up the square root of 75. 25 and 3. And then you think, well, which of those is on my list as a perfect square? That's the 25. And we know what it is. It's 5. And now that the 5 doesn't have a radical, we multiply the 3 times the 5. And we have it, 15 square roots of 3. Now, Sometimes people wonder, well, doesn't that mean these are really very different numbers? 3 square roots of 75 and 15 square roots of 3? Well, let me show you. 3 square roots of 75 and 15 square roots of 3. It's the exact same numerical value. It just looks differently. So we're just manipulating it. And that's what Algebra 2 is about. We're supposed to become master manipulators of numbers and letters in algebra. And that's what we're doing. Please write down number 3. 3 square roots of 8 times 5 square roots of 50. Now, I have talked to you before about how mathematics is a, hey, if I just did this, this would look like a problem that I already know how to do. So I look at this one and I think, well, I should do the multiplication, because then it'll look just like the last problem that we did. 3 times 5 is 15. 8 times 50 is 400. Now, I realize 400 is not on our list. Does anybody recognize that as one of our perfect squares? And if you do, could you unmute and let everybody know?
20.
It is 20 squared. So if you knew that, then you could go ahead and write this as 15 times 20 right away. But let's just say that you realize, well, I need a perfect square on there. Oh, 100 goes in there 4 times. So if you didn't know the square root of 400 is 20, you could still get the right answer, because this is 10 and this is 2. And 10 times 2 is 20. So you'd still be able to get there even if you didn't find the biggest one. It just makes the math much easier if you do use the biggest one. So 20 times 15 would give us 300. Please write number 4 down. The quantity 4 square roots of 7 squared. All right, this is really, really important. We have to remember that exponents are used for the closest thing to their left. And the closest thing to the left of that little 2 is parentheses. So we have to write this down twice. Now, I don't want that to be in the glare spot there. I suppose it still is. That's a little better. Now do you see how this looks exactly like the problem that we just did? So somebody unmute and tell me what we should do.
4 times 4 and then 7 times 7.
4 times 4, that'll give us 16. The square root of 7 times the square root of 7 will be the square root of 49, because you multiply square roots times square roots and integers times integers. Hey, wait a minute. I think there's something special about the square root of 49. Can somebody unmute and tell me what that something special is?
It's a perfect square.
It is. So we just grab a calculator and punch in 16 times 7, or do it by hand quick, because it's not a toughie, and we'd get 112. This is what's so cool about math. It's like we have our own secret little language. This says 112. That's what this says. But you have to know how to do the math in order to get there. So very, very cool the way that we can manipulate our numbers and our letters. Oh my. That looks bad. But here's the important part. When we are simplifying fractions, the biggest problem with these is if there's a radical in the denominator. Oh, phew. This one doesn't have one. Oh, that's good. So now all we have to do is figure out, is the square root of 20 something we can simplify? And once we simplified that, is there something more we can do to this fraction? So you leave the 3 alone, you leave the 2 alone, and you leave the 6 alone. But you think about the 20. I would like somebody to unmute and give me the biggest perfect square that's going to go into 20.
4.
That's it, isn't it? And it goes in 5 times. Well, we're going to be able to do a little bit because we know that this is 2. So we can multiply the 2 times the 2. And now the question is, can I go farther with this problem? Can I simplify this so maybe there isn't a denominator anymore? So here's what we have to ask ourselves. These are the integers, 3, 4, and 6. Is there a number, an integer, that would divide evenly and nicely into 3, 4, and 6 all at the same time?
No.
Matt says no. Everybody else is a no? You're right. There isn't. 3, 4, and 6, there's nothing we can do. We're done. We are done. That's as much as we can do with this problem. Because the integers that we see, not the radicals are separate, cannot be reduced from what we see here. Go ahead and write down number 6, the square root of 3 over the square root of 9. There's definitely more than one right way to solve radicals. But I want you to look at this one and ask yourself, where's the problem with this? What part of this would say, I am not simplified? Anybody see it? And if you do,
Radical in the denominator.
there's a radical in the denominator, exactly. We don't really care that there's a square root of 3 in the top unless it's something we can simplify. But there's a radical in the denominator and we absolutely cannot leave it there. So the question is, do we know what the square root of 9 is? And what is it? Somebody please unmute. Square root of 9 is?
3.
Yep. Now I ask myself, square root of 3, anything I can do to that? And I don't have any perfect squares because 4 is already too big and 1 squared is not helpful, so that's done. Now, here's another way to do this problem. You notice, hey, they separated that. Maybe they're trying to hide something from me. Maybe they didn't want me to see that I can reduce that fraction because 3/9 is 1/3. Now if I do that, I still have to think, well, I've got square roots going and a fraction here, so I'd have to separate it into the square root of 1 over the square root of 3, but the square root of 1 is just 1. And then we get to this point, which is also going to show up in your homework today that you're going to do. So I have 1 over the square root of 3, and I know I can't leave the square root of 3 in the denominator. So do you remember how we took care of that earlier this year? And if you do, could you unmute and let everybody know?
Square them both.
In a way, that's what we need to do. Because we are going to multiply the top and the bottom by the square root of 3. So that will give us the square root of 3 on the top and the square root of 3 squared on the bottom. And we realize, well, those are inverses. Square root and squaring, those are going to make each other disappear. So it took quite a few more steps, but do you see how it's exactly the same answer? And that's because, like I said, sometimes we're going to run into this situation of we have a radical in the bottom and we have to get rid of it, and it's not a nice perfect square. So we needed to do that both ways. This one. Anybody notice something that maybe they didn't want us to see?
It can be reduced.
Exactly. So it always makes me suspicious when the book already separates those two. And I start thinking, maybe they didn't want me to notice, oh, look at that. 4 goes into both of those. Now 2 is not a perfect square and 3 is not a perfect square. But I need to separate them because the problem is that square root of 3 down there in the bottom. And since I just talked about this in the last problem, can somebody tell me what we should multiply the top and the bottom of this little fraction by so that we don't have a radical in the denominator anymore?
The square root of 2.
Oh, the denominator is our focus.
Square root of 3.
Right. The numerator, the top of the fraction, it can be a radical. We don't care. But we cannot have a radical in the denominator. So no square roots in the denominator. So this is now the square root of 3 squared. On the top, square root times square root gives you square root. So square root of 2 times the square root of 3 is the square root of 6. But here's the big deal. What is the square root of 3 squared? Somebody unmute. What's the square root of 3 squared?
3.
It is. Now, we got to ask ourselves, are we done with the 6? Well, there's no perfect squares. I mean, 4 is the only one that we could try, and it's not going to divide evenly into 6. That's done. That's as much as we can do. So this first step, really important. Noticing, hey, they didn't want me to see that I could reduce 8/12, and that makes the math a little bit easier. Look at that monster. Go ahead and write that bad boy down. 4 plus the square root of 32, all divided by the square root of 2. So we have 2 things that are issues here. But what we should focus on first is the big problem. Somebody unmute and tell me what the big problem with this fraction is.
Radical in the denominator.
Exactly. So we do exactly what we did in the last problem. We look at the denominator and say, okay, I'm going to need another one of those. Have to have it. It's the only way I'm going to make this work. This will now be the square root of 2 squared, which I know is 2. Now notice I didn't even bother with the numerator yet. And that's because that was the really important part, making sure that there's no radical in the denominator. Now I have to distribute the square root of 2 to both the 4 and the square root of 32. But here's what I know. You can't take a radical times an integer. Well, we can't, but we can write it 4 square roots of 2. I mean, then everybody will know, hey, we tried to multiply. That's what we did. And then the square root of 2 times the square root of 32. 32 times 2 is 64. Wait a second. I think square root of 64 is special. What is it, everybody? Unmute and let me know.
Square root of 8.
It's 8, just 8. When we do the square root, get rid of it, and that'll give us 8. So this can become 8 plus 4 square roots of 2. we tend to put the radical in the back. I mean, you see how it came up here? Mathematicians usually put the radical in the back. Now we might not be done. Check your integers, 8, 4, and 2. What could we take out of all three of those integers?
2.
Yes. So we want to do it the right way so that anybody that's looking at our paper knows, hey, we knew what we were doing. So here's how to do it the right way. You factor out a 2. Because we all know we want to cancel. But canceling is a form of division. So before you can cancel using division, you have to see multiplication. And here it is right here, 2 times. So now we can cancel the 2's. And we'll be left with 4 plus 2 square roots of 2. And we've got it. So that radical in the denominator, that is a really big deal. Next problem. Go ahead and write that one down. This one's ugly. Square root of 5 plus 3 over 4 minus the square root of 7. So this would have been one that they probably scrapped at the end of geometry last year. Here's the problem. If we just multiply this denominator by the square root of 7, it's not going to leave, because then we'll have 4 square roots of 7. So what we have to do is try to figure out a way to get rid of both the 4 minus the square root of 7, both of those terms, by multiplying by something. And here's what we use. The fancy name for that is the conjugate. And notice how the first term is the same, the last term is exactly the same. The only difference is that this had a minus and this now has a plus. So what we just did was we made that sum and difference pattern. And when we did FOIL on that in chapter 4, we know that the middle term drops out. Well, that means all this square root stuff is going to drop out. That'll be perfect. That's what we need. But what we do to the bottom of a fraction, we also have to do to the top. That's how fractions work. We really just want to multiply by 1. And 4 plus the square root of 7 over 4 plus the square root of 7 is 1. Now, our focus needs to be that denominator first. So don't even do anything with the numerator yet, the top of that fraction. We want to make sure that we're not going to have anything weird happen down there on the bottom. First times first is 16, because we just do FOIL. Outside times outside will be 4 square roots of 7, but inside times inside will be minus 4 square roots of 7. So we don't even have to write that down. Those two are going to cancel out because one's a minus, one's a plus. Last times last will be minus the square root of 7 times the square root of 7, which you might just want to go think of that as the square root of 49. So 16 minus 7, and then we give ourselves one of these. Yes, we're good. Yes, look at that. No more radical down there. Now that doesn't mean anything about the numerator. We're probably going to have some pretty awful looking stuff up there. But remember, the big deal with fractions is you can't have a radical in the denominator. Now let's see how ugly the numerator is. First times first, 4 square roots of 5. Outside times outside, plus the square root of 35. Inside times inside, plus 12. Last times last, plus 3 square roots of 7. Now, we want to ask ourselves, square root of 35. Is there any perfect square that's going to divide evenly into 35? Well, 6 squared is 36. That's too big. 5 squared is 25. 4 squared is 16. 3 squared is 9. 2 squared is 4. Oh, ish. So what that means is this whole thing up here, there's nothing else we can do with it. So I'm going to give myself a little bit more space. What we might want to do is make sure the 12 goes in the back, since all of these have radicals. And it doesn't matter. The order doesn't matter up there. But there's nothing we can do with that. Unless every single one of these had a number in front of it that we could reduce with 9. But it doesn't, because this is 1 square root of 35. So 9 definitely isn't going into 1. It's not going into 4. 3 and 9, those would be reducible, but it has to be in all of them in order for us to reduce. And it's not. So that was the toughest one for today. So here's what I need to know. If you want another one like number 8, you want another one like number 7, please unmute and let me know, and I'll make up some new ones. So everybody believes they have it. This is the simplifying square roots worksheet, and I know I handed it out to the hybrid learners that were here, but if you lost it, if you don't have it, you're going to take a notebook sheet of paper and you're going to go down here to the black digital copies of worksheets and handouts. Down we scroll. And here it is right here. Algebra 2 Simplifying Square Roots Worksheet assigned today, December 9th. You click on that, and you'll see all the problems on the worksheet, and you can write your answers on normal notebook paper. And you'll have all of those. Now, I'm not going to put the key to this up immediately. I think I'll wait until tonight and then put it up so that everybody has a chance to try these. And don't forget about your slip of paper with your perfect squares on it. That's really important because, like I said, when we get to the test, you can't use it. And that means some of these have to just pop into your mind right away. And the best way to do that is to have to look them up a few times so your brain says, let's hang on to this information for the future. So this is what you need to work on today. Feel welcome to stay signed on and work on it and ask questions as they come up. Or you could pop off, and if you have a question before the end of the hour, pop back on. Totally up to you.